Hello everyone, welcome to Introduction to Photonics lab session. This is Nirjan and so today we'll do experiment of 4. We have done 3 experiments till now, so today we'll do experiment of 4, which is interaction of light with matter. So it consists of 4 sub experiments. So first experiment will be, we'll just have some color filter and we'll pass red light as well as green light and see the transmission of the transmittivity of the color filters. So we'll check the different color filter, yellow, red, blue and green, and we'll see the transmittivity for red and green laser. Okay. And the second part will be seeing the fluorescence in rhodamin dye. So we have 2 rhodamin dyes, one is rhodamin 6G and rhodamin B. So we have 3 different concentrations, and we'll see the fluorescence in both the dyes. Third one, we'll see the absorption. So how much absorption is happening in the rhodamin dye. So in all the 3 concentration, we'll see how much, we'll measure the incident power, we'll measure that power that is transmitted. From there we'll get the power that is absorbed in the dye. And the fourth experiment we'll see, okay, of this absorbed power, what is the power that is being emitted back. So we'll see the fluorescence. So these are the 4 parts. So I'll start this lab experiment by explaining you all the components that are needed in this for this experiment. You can see that on this optical breadboard I have 2 laser sources. So this one is actually 650 nanometer, so it's a red laser source, and this is 532 nanometer, so this is green laser source. Okay, so you can see this one is green laser source and here it is a red laser source. Okay, so green laser source, both are diode laser. So this is a diode laser, fiber, this laser power comes to here. So for coupling it to fiber couple mount over here, so it comes to the green lasers. Similarly for red, so this is a driver here for red laser, okay, but red laser is directly a diode laser, no need of coupling into the fiber. So it's directly, power is directly being generated here. Okay, so now this laser is 5 milliwatt laser, this power of this laser is 5 milliwatt, but this is very high end laser, so it can go up to 1.5 watt. Okay, so generally for this, that's why, because it's very high power, we generally have laser goggles. So laser goggles, so this is for green laser, so it allows all the light to pass, but it doesn't allow the green to pass. You can see, not allow this green laser to fall onto our eye. So this is just for safety of our eye. And red, it allows red to pass. So for red there has to be separate goggles for red, but we don't need red, even don't need green in this case, because we will be operating it for lower power. Then we have 2 more laser sources. So these 2 are diode laser, so just available, you can easily buy it on any online platform, just 500 rupees. Of this one is red laser and this one here is green laser. So we will be using this also, but for the mainly for any measurement of power or something, we will use those 2 lasers, but for this laser, handheld laser, we will use only for just qualitative study, because for quantitative this cannot give a stable laser output. That's why this is just for qualitative study in case we need it. Okay. Then here we have some color filters. So we have a yellow color filter, blue, red and green. Okay, so basically these are made of dyes itself. So this is a color filter mount, so we'll use them one by one, mount them on this mount, and then this is iris diaphragm for alignment. Okay, so now we have rhodamin 6, so this is rhodamin B. So we have 3 different concentration of rhodamin B, you can actually see. So this is our 3 different concentration, very high concentration, medium concentration, low concentration. We will just do the qualitative study of this fluorescence from this dye. Then we also have rhodamin 6G. So I have 3 different solutions of rhodamin 6G, again high, medium and low. So we will do a study of fluorescence of this as well. So this both these solutions were made in ethanol. Okay, so we have one more ethanol solution also. So these are cuvettes, all these solutions are kept in cuvettes. So cuvettes is generally used to study the fluorescence and absorptions of any liquid. So transmission, fluorescence, absorption of any liquid. So this is plastic cuvette, disposable plastic cuvette. Generally in market there are glass cuvettes also available, but in this case we will use this plastic cuvette. So this is a power detector, and this is a power meter, so which will show the reading. Okay, and we also have lens tube to reduce the background noise. So if we put it on the power detector, it will block the background noise. So this is a lens tube. So this is a variable neutral density filter. So this actually is called neutral density because it brings in the same attenuation to all the different wavelength and visible light. So we will use it to vary the laser power of red as well as green. So now the first part of the experiment, so that would be seeing the transmission to different color filters. Okay, so we will see the transmission through different color filter, first from green light, then from a red laser source. So for a green laser source, you can see a green laser source coming out here, and here I will mount the filter. For now I have not mounted anything, and that is falling onto the detector. Now you can see the reading into the meter, power meter, and it is giving 3.6 milliwatt. So this is the laser power I am putting right now. Okay, so now what I will do is introduce each filter one by one, and we will see what happens to the transmitted power. So we will start the experiment with the red filter. Okay, so I will mount the red filter into the filter mount. So you can see the power has reduced from 3.6 milliwatt to 0.02 milliwatt. Okay, so red filter is not allowing the green light to pass through. So let's move on to the next higher filter, which is a yellow filter. So for yellow filter, so power is little bit more, it's like 1 milliwatt, around 1.02 milliwatt. Okay, so what if I reduce, so this was yellow filter, so now what if I change this yellow filter to green filter? So this is my green filter. You can see the power is sufficiently high, 1.19 milliwatt. Okay, fine, not much difference. You can find that's not much difference, yellow and green, because they are pretty close. So maybe the filter design, but you can still say it's allowing, the green filter is allowing green light to pass, and it's blocking red. And let's see what happens to the blue filter. So for blue filter also you can see it is 0.32 milliwatt. So you can easily, from here you can easily say that the green laser source is being allowed only by the green filter, while red and blue filter are blocking the green laser. Yellow filter is also allowing a significant amount of it, but still a green filter is the best for if you want to block other block other wavelength, and only allow green color to pass. Okay, so now we will do the same experiment with the red laser. So you can see the red laser I have adjusted so that it is also the same power, 3.6 milliwatt. This is a laser power of the red laser, and I'll again start with the red color filter. So this is a red color filter. So the power you can see is 2.46 milliwatt. Okay, so you can now let's go for a yellow filter. So power is much reduced here, and it is coming to 1.48 milliwatt. Okay, for yellow filter. Then for a green filter, power is further much reduced, and it is coming to 0.934 milliwatt. So you can see that power is reducing as I am going away from the red frequency. So now this is blue, it is farther away, so it will give further less for the red color laser. So it's giving 153 milliwatt. So from here you can say that the red color filter is best suited for allowing only red color to pass and blocking the other wavelengths. Okay, so this will be the first part of this experiment. Okay, we'll move on now to the second part. So in the second part of the experiment, we'll observe the fluorescence phenomena. So for that I have already showed you, I have two rhodamine solutions. So I have rhodamine 6G and rhodamine B, and for each I have 3 different concentration, as well as I have ethanol. So just see that there is nothing happening in pure ethanol. There is only something happening if I dissolve rhodamine dye in the ethanol, then it shows the fluorescence phenomena. So I'll actually show you that it happens only at one wavelength, it doesn't happen all different. If I put a green laser light, you will be able to see the fluorescence, but if I put a red laser light, you won't see any fluorescence phenomena happening. So let's see, go forward and see the fluorescence phenomena. I just will have to switch off the light so that you can better see the. So now, if I use a green laser and I shine the green laser on the rhodamine dye solution, you can see that it's emitting out orange color in all direction. So actually it is a green laser, you can see this is green color, but if I am passing it through rhodamine dye, what I am getting is the orange color. So this is the fluorescence phenomena that we have been talking about. So this is a little lower concentration, and here also you can see that emitting orange light, but only that it will just lesser intensity you can get here. Further here, this is also same but very low concentration, still intensity is reduced, and you can also see that the green light, laser light is passing through, and you can see the green laser light spot over here. But what's emitted from the cuvette, that emitted, scattered from the cuvette, you can see in all direction on the paper down here, that is orange. So now if I put it through ethanol solution, so there is no fluorescence phenomena happening here. So green light remains a green light, okay? But in each of these cases you can see the orange light that is being scattered in all the direction. This is a green laser. Okay, so this was the first observation. So one more thing that can be observed is, in very high concentration, if I pass green light, barely any light goes inside of it. Okay, now if I use a little lower concentration and again pass a green light, you can see some of it is you can see the decaying inside the solution. It's very, so it is getting absorbed as it gets transmitted through the solution. Okay, now if I reduce the concentration further less, you can see it completely passing through. Very less of it is getting absorbed, most of it just passes through the solution, because in this concentration is so less that there are not enough rhodamine molecule to absorb this light. So very little amount of the light incident is absorbed, and those absorbed light is scattered as fluorescence, but most of the light is just transmitted through, which you can easily observe in the gradual change in the concentration. So let me show you again: highest concentration, medium concentration, and the lowest concentration. So similarly we can see whether we can see any fluorescence due to red light. So we'll try the same experiment with red light. So this is red light, you can easily see, but there is no change in color for any of the concentration solution, either ethanol or any of this concentration of rhodamine dye. So rhodamine is not showing fluorescence at the red wavelength, so it is only showing fluorescence for green wavelength. Okay. Similarly, rhodamine's B solution, this also has a pretty similar absorption and emission wavelength, so very little difference is there. So for red it won't show any fluorescence. So three different concentration are there. So this is a high, medium, low. So high, medium, low, and none of the concentration shows fluorescence. But now again it will show fluorescence for green light, green wavelength. Okay, so it will show fluorescence for the green light. So all that concentration is showing the fluorescence for green light. So next part of it will be seeing the absorption of the green light. So we saw that the fluorescence is only shown by green light, by rhodamine dye shows the fluorescence only for the green wavelength, and it emits the orange wavelength. So now for the third part of the experiment, we will use green laser source and see how much of its power is getting absorbed by the different concentrations. So we will just characterize it a little bit, absorption characterization. So let's see the reason behind the fluorescence, why there is a color change. We are putting in green and we are getting a different wavelength, why is there? So in class, as I already explained, for in the optical amplifier here in this picture itself, is shown that there are three: ground state, high state, and metastable state. So the electrons are getting excited from the ground state by 980 nanometer level, as 980 nanometer wavelength, to a higher energy state, from where it decays back to a metastable state, and then from metastable state it decays back, it comes down to the ground state, emitting a wavelength of a higher wavelength. Okay. So, in this case the same thing is happening. So, when you shine a green laser, the electron in rhodamine diamolecule gets excited from the ground state to a high energy state, then it comes back to a metastable state, from where it gets back to the ground state, emitting a higher wavelength because of the low energy gap in this case. So, the third part of the experiment will characterize the absorption happening in the rhodamine dye. So, for absorption what we will do is we will put some measured amount of laser power, instead some measured amount of laser power. We will see the transmittance, and the subtraction of these two quantity will give us the absorption that is happening. Okay. But only problem here will be that some light is also getting scattered along with getting absorbed. So, for that, to characterize the scattering, we are having some reference here, just a reference, and they will use pure ethanol as reference. So, we will take a reading with pure ethanol, and then we will take a reading with rhodamine, and the difference between these two readings will give us the absorption due to rhodamine. Okay. So, I will start. So, now so this is the laser power 36.6 milliwatt. So, right now the laser power, that is 36.6 milliwatt. So, I will take reading for all the different concentration as well as ethanol. So, I have all of them tied up together here, low highest concentration of rhodamine, medium, low and pure ethanol. So, I will start with the highest concentration of rhodamine. So, now this is transmitted power here is 4.15 microwatt. For the medium concentration, transmitted power will be 11 microwatt. So, you can see that transmitted power is more for the medium concentration. Now, if I go to further to the lower concentration, so for lower concentration, transmitted power is 5.14 milliwatt. So, it is a pretty high compared to the medium concentration. Now, this is our reference ethanol. So, for ethanol, so 29.1 milliwatt. Okay. So, this will be our first reading. So, for the second reading we will take at a different laser power. For that we will use attenuator here. This is a neutral density filter, variable neutral density filter. So, we can vary the laser power coming out of it. Okay. So, it is called neutral density because it allows attenuation, equal attenuation for different wavelength of light. So, it is neutral for it is independent of wavelength. So, now what I will do is I will reduce the laser power. So, once the laser power passes through this, it will be a little bit lower power than that. So, now you can see from 36 it goes to 33.9. So, again we will repeat the same process for 33.9 milliwatt. So, I will take one reading for highest concentration 6.06 microwatt. Yeah, 6.06 microwatt. So, I have to make sure that this falls onto the liquid, not on the sides of the cuvette. So, I have to adjust it properly and I have to make sure that this falls normally onto the cuvette. Okay. So, on medium it is 12.12 microwatt transmitted power, and for low concentration of rhodamine it is 4.85 milliwatt. And then again our reference solution ethanol, it is 27.4 milliwatt. So, now I will repeat the experiment once again by changing the power. So, this time I will reduce the input power furthermore, 30.01 milliwatt. So, reading for the highest concentration is 4.24 microwatt, 4.24 microwatt. Then for the medium concentration 9.62 microwatt. Lowest concentration 4.32 milliwatt. Then for our reference again 24.1 1 milliwatt, 24.1 milliwatt. Change the power level again. So similarly, we can do it for different power levels. Let me do it for a very low power level. So let's go to 3 milliwatt. So this is 3.02 milliwatt or 3 milliwatt. So for 3 milliwatt, so transmitted power for the highest concentration of rhodamine is 0.54 microwatt, 1.14 microwatt, 0.428 milliwatt for the lowest one, and for the reference solution we have 2.39 milliwatt. 2.39 milliwatt. Now just take one more with the lowest concentration possible with this neutral density filter, lowest not concentration, lowest power possible. So that will be 13.02 microwatt, 0.14 microwatt. Then for medium, I'll show 0.17 microwatt. Then for the lowest concentration of rhodamine, two microwatt. 2 microwatt. And for ethanol, our reference solution, very difficult to track the ethanol, it is 10.72 microwatt. Now what we need to do is, we'll find out the absorption by taking the difference in the reading of our reference and the rhodamine, and then plot it against the free space laser power, so which we had measured. So from the plot, what we'll have to see is how the saturation happens in the solution. So in the dye, there are fixed number of dye atoms. So if the laser power is so much to excite all of them to a higher state, no matter how much you increase the laser power beyond that, there won't be any more excitation. So fluorescence won't increase after that. So that's where you will touch the saturation. So that's the same thing that we should observe using this phenomena, this result. So that's it for the third part. So now we'll move on to the fourth. So fourth part, we'll try to capture the fluorescence. So instead of capturing the transmitted light, we'll try to capture the fluorescent light, and you can see that by observation that fluorescent light is coming from all the directions. So what we'll do is, to get the best fluorescence power, we'll capture light from just one of the direction, and from that we'll try to put filters in between and try to see which filter allows the fluorescence light to pass the best. So that will be the last part of this experiment. Now in the fourth part of experiment, what we have to do is, we have to characterize the fluorescence. So fluorescence phenomena is independent of the direction of light. It happens in all the direction and random. So because it is due to the spontaneous emission, and spontaneous emission can have any direction and any phase. So that's why what now we are trying to characterize. In the previous experiment, see the transmittance. Now what we will do is, we will see the fluorescence directly, not by doing the incident power minus transmitted to get the absorbed power. We will directly see what is the fluorescence and what color fluorescence it is. Okay. So for that, the very simple experiment that we have here is, again the same green light falling onto the cuvette with rhodamine dye. So I have chosen one concentration, highest one here. Okay. After that, I placed one power detector here, and the same setup, exactly same. Only thing that this time the power detector has this angle, so that I just measure the fluorescence, because here it contains the transmitted light also, but here there will be very less transmitted light. Whatever light, green light will be there, will be due to the scattering. Okay. So most of the light collected on this side will be the fluorescent light. So now what we will do is, so it is coming 163.8 microwatt. This is the intensity that is giving. Okay. So now we will put in filter one by one, and we will see and we will see what is the which filter is allowing the fluorescent light to pass the best. Okay. So, we will again start in the same order. We will try with the red filter. So, I have a red filter here. So, I have a filter stand. I will fix the red filter into the filter stand and I will place it in between the detector and the cuvette, carefully without disturbing the cuvette. Okay. So, for red filter you can see the reading is around 51.8 microwatt, 51.8 microwatt. Okay. So, now I will remove the red filter and now I will put the yellow filter. So, you can see the reading is 135.8 microwatt. So, it is obviously more than the red filter. So, red filter, so the fluorescent light is closer to the yellow color than red wavelength, yellow wavelength than red wavelength. Now, let us try for the green wavelength. What happens if I put in the green filter? So, again without disturbing the setup, I have put the green filter in place. So, now, so once the fluorescent light passes through the green filter, the power observed is 35 point, or you can say 35 microwatt, is fluctuating a little bit, 35 microwatt we can call it. So, you can see that for yellow you got the maximum. So, you can see that the fluorescent light has a wavelength in the around yellow wavelength region, and that was our observation for by in examination by naked eye. So, we observed that it was giving something orange. So, that is why we got the maximum transmission through the yellow color. So, let us check for the blue also. So, blue is much farther away, and let us see, we expect it to be low because we have already seen that for red as well as green it is lower. So, blue is further away, so it should be further low, and let us verify for the blue, and you can see it is much less actually, and 12.12 or 12.1 microwatt we can call it. So, 12.1 microwatt we are getting for the blue filter. So, you can say that the fluorescence that is happening at the yellow wavelength, while in the first experiment we saw that the this input was allowing most transmittive was for green filter. So, the input is green and the fluorescent light is yellow. So, that is what we conclude from this experiment. So, all the 4 experiments, we can summarize that light falls onto the atom, excites the electron to a higher energy state. From there it decays to a intermediate metastable state and releases the energy in form of heat. Now, from metastable state comes back to the ground state, and during this transmission the energy, leftover energy, is emitted in form of secondary wavelength, and that wavelength is little bit higher than the previous input wavelength because there is a lower energy this time, and this wavelength that is emitted, and that is what we see as a fluorescence. So, this is the fluorescence phenomena that we observed today, and it has multiple use. It is not just an experimental study, it is already being used in much of the scientific world to study it. In sensors it is used. So, there are many sensors which depends on the fluorescence of dye molecule. So, you add a dye, then to detect what is the concentration of particular light, you put on a light which will make the dye give out fluorescence. From there you will get the concentration of particular light that you want to detect. It is even used in, you must have seen a UV painting. It is called dark room painting, where you just paint with the UV paint and then you switch on the UV light. So, UV light is not visible to us, so the room will still be dark, but the fluorescence from this paint will glow because due to fluorescence this UV wavelength will be emitted back as a secondary wavelength of a little higher frequency which lies into our visual spectrum. So, we can see that. So, the paint will glow and the painting will be able to see the painting in the dark, as well as it is used in Thor labs. You can see Thor labs laser viewer. In that also same mechanism is there. For UV light, you put a UV laser beam, you put a laser viewing card in front of UV laser light, because the UV laser light is falling, and then the fluorescence, due to fluorescence, the higher wavelength will be emitted, and that higher wavelength actually lies into our visual range, and we are able to see the laser spot. So, there are multiple uses like this, and okay, thank you.